Just to get a better feeling for what what this data set looks like, I converted it so it could be read by and plotted in a three-dimensional viewer. That viewer is available at this URL, which is part of the resources for this class. And that viewer allows us to take the data and browse it in 3 dimensions. And this will point out that depending on how you rotate in 3 dimensions, these different clusters actually may have different separations. So let's actually see what happens there before we look at the all right, so here we have this 3-dimensional plotter, plotviz. It's got exactly these 1,000 points, and it has this tell you how many points there are in each of the collections: 342, 331, and 327. And if I move my mouse around, I can rotate this section. You can see, depending on how I look at it, like here, it's very clean. Actually, here's where Z is perpendicular to the screen. So actually, you just get the XY projection slightly rotated. And so we know already that's pretty clean. In this particular, in some of these other ones we're looking at, is pretty messy. So all that says is that if you want to disentangle what things are going on, and those things are in high dimensions, looking at 2 dimensions, or even, of course, 3 dimensions if it's higher than 3, may not tell you that very well. In 3 dimensions, as you're using distance to define your separation, it should be fine. And here we're effectively doing that. So here we can browse it and see, which makes us in. We can see these green ones are rather cleanly separated at the bottom here. And depending on, say, here's a very clean separation between the 3 segments, 3 clusters, 3 classification groups. So that's that. So you can play with that if you download that software. Now let's go back to the slide. So the next slide actually just shows a screen dump of actually just what we did. So it actually shows you one of the cases, which is very clean, with the z-axis almost directly out of the screen. So you get an x and a y, although it's not exactly, x is not exactly horizontal and y is not exactly vertical, because I was just playing around and then just stopped when I felt I wanted to. So that's that slide. Here's here's just another example of this with not quite so cleanly done. Z is a little off the is entered into the discussion a bit more, and here's a case where actually Y is nearly out of the screen, and so you have X versus Z when the separation is by no means obvious. So that's just a salutary warning or a fun or what, I don't know what you want to call it, but trying to find structure in high dimensional spaces is not so trivial, because that structure can be gotten from dimensions you're not looking at. Now we come on to the next part of this Python, and it points out that the final line in the driver is calling another function, dating class test, with a single argument of the value 0.1. And that one, if you'd actually looked at the Python I run, it prints out a few things at the end, which is the so-called total error rate, which is 5% or 0.05, and the number of bad points, which is 5. So what is this doing? So this is actually doing something which is pretty important. Namely, it's dividing the data into a set used to classify and a set used to test the classification. And the parameter 0.1 determines how you do that division. And it is such that 0.1 is the fraction of points that you're going to use to do the test, which implies that 0.9 is the fraction that you're going to use to do the classification. So that means where you just use Harrington's values for the classification. This particular code is extremely simple. If you look at dating class test, it actually takes the first fraction, or which is 100 points, because we know it's 1,000 points, so 0.1 times 1,000 is 100. So it takes the first 100 points and use them as the test set, and the next 900 points is the classification set. That wouldn't be a good idea if there was some sorting, if they were not randomly sorted. For instance, if there's a woman who'd done the dating classification and put all the people she disliked at the beginning, then you wouldn't be very good to put all the to have a bias in your testing set. Your testing set needs to be unbiased. Therefore, it needs, in general, what you'd ought to do is to randomize the points and then choose the first 100. So the results of this, what it does is it takes those 100 points and it calculates using the KNN classification algorithm with actually 3 nearest neighbors, and it calculates the classification, and it compares the nearest neighbor classification with Harrington's classification, and if they're different, it counts up the number of the numbers that are different, and out of the 100 points, 95 get the same answer for the between Harrington's classification and the nearest neighbor classification, and 5 disagree. So that's what the number bad being 5 is. And that's the fact that these are not exactly right is almost inevitable, because if you just look at those pictures and take a point near the, let's take this one where it's clean. No, this is the cleanest one. We take points here which are clean, points which are at the edges of the regions, whether they're classified as one cluster or another is, or one given one classification or another is in the eye of the beholder, is rather ill-defined. And so you're bound, you'd expect to get some error rate there.